सर अनम्यूट करना पड़ेगा। हेलो।
Hello.
Yes, sir. Good afternoon, sir.
Good afternoon.
Okay. So I welcome all the faculty member and participant in the second session of the third day of the recent advances in composite material. So we have expert from the MNIT Bhopal, Dr. Rajesh Purohit sir. He has more than 17 years of experience in the teaching field. His area of research is basically metal and polymer matrix nano-composite for the automotive, aerospace, and biomedical application. Forming behavior of the nano-composite, unconventional machining, rapid prototyping, biomaterials, nanotechnology, testing, and the material. He has completed 2 research projects as well as the 9 consultancy project. He has published more than 200 paper in the various domain like conferences, various general, and recently he is guiding 5 students in the PhD program as well as the more than already guided 40 plus student in the MTech program. So I welcome Dr. Rajesh Purohit sir for this session.
Thank you very much. Thank you. And good afternoon, everybody. So should I start?
Yes, sir. Yes, sir.
Okay. I shall share my screen. PPT.
2 minutes.
My presentation is visible or not?
No, sir, not visible.
Not.
No, does not have anything. नहीं अभी नहीं है, कभी नहीं है। तो हमको भी अभी
Now it is visible.
Yes, sir. Now it is visible.
Now it is visible. Just slideshow. Yeah, I think it is now. Okay. Okay. Now it is slideshow is visible, na?
Yes, sir. Visible. Perfect.
Okay.
Yes, sir.
Okay. Good afternoon, everybody. So my presentation will be on development, testing, and analysis of the aluminum matrix nano-composite for automotive application. Okay. So this presentation will include introduction, literature review, research objectives, equipment used, methodology, experimental work, result and discussion, microstructural examination, conclusion, and references. So first, I start from the basic. What is nanotechnology? We are trying to discuss nano-composite. So first, we should know what is nanotechnology. So nanotechnology is the science of manipulating matter on an atomic and molecular scale. It deals with the structures size between 1 to 100 nanometer. And nanocomposite is a multi-phase solid material where one of the phase has 1, 2, or 3 dimension of less than 100 nanometer. Actually, 1 to 100 nanometer is considered under the nanoscale. So if a size is more than 100 nanometer, then it goes into micron or larger scale. It is not nano. Okay. The mechanical, electrical, thermal, optical, electromechanical, chemical, catalytic properties of the nanocomposite differ markedly from that of the component material in the larger size. Okay. The nanocomposite differ from the conventional composite material due to the exceptionally high surface area to volume ratio. of the reinforcing phase. That is very important. Surface area to volume ratio. Because as we go on reducing the size of the particle, surface area drastically increases or volume is decreasing. So the ratio of surface area to volume is drastically increasing. So that make a significant effect on the properties. The reinforcing aluminum matrix with much smaller particle, submicron or nano size range is one of the key factors in producing high performance composite which yield improved mechanical properties. Recently, the nanomaterials uh, have been the subject of enormous interest, notably due to their extremely small feature size uh, and wide range of industrial wide range of industrial, biomedical, material, automobile, aerospace, defense, and electronic applications. The nanoparticle reinforcement enhances optical properties, dielectric properties, heat resistance, or mechanical properties such as strength and resistance to wear and damage. Basically, what happens as we go on reducing the size up to nano level, the crystal defects are goes on decreasing and they reach almost to nil. So as the crystal defects is reduced to nil, basically the what strength we get on the material is equal to the bond strength of the material because of the no crystal defects. So that's why we get at nano size or smaller size, we get very high mechanical properties. That is main reason of materials or nanoparticles, etc. or nanofibers. So that is the reason. As we go on reducing the size to nano level, the strength goes on increasing of the particle or fiber, etc. The aluminum alloy provide a good matrix for the development of nano-composite because of low density, high corrosion resistance, ease of fabrication, and good thermal conductivity. Super tough and ultra high temperature resistant materials are in critical need for application under extreme conditions such as jet engine, power turbine, catalytic heat exchanger, military armors, aircraft, and spacecrafts. The amount, size, and distribution of the reinforcing particles in the metal matrix play a key role in limiting the overall properties of the composite material and can be used for the automotive application. The aluminum matrix composites of high strength at elevated temperatures are very useful in aerospace and automobile applications. Now, what is basically composite material? In composite, basically there is a matrix material which is continuous phase, which is reinforced with the particle reinforcement, and then we get the composite material. So matrix is basically the continuous phase and particles are the discontinuous phase. As a reinforcement, basically it is mostly used to increase the strength. That's why it is called reinforcement. And this type of composite are basically particulate composites. And other type matrix is reinforced with fiber, that is long fibers. So this is called fiber reinforced composites. Okay. In type of composite material, we have basically on the basis of matrix, we can categorize in three types of composite material. If metal is the matrix, it is called metal matrix composite. If ceramic is the matrix material, then it is called ceramic matrix composite (CMCs). And if polymer is used as the matrix, then it is called polymer matrix composite. Similarly, we can also classify on the basis of reinforcement. If particles are used as reinforcement, then particle reinforced composite. Fiber are used as reinforcement, then fibrous composite. And if this is a full sheet of the fiber or some lamella are there, then it is called sheet or polymer composite basically. So in metal matrix composite, predominantly metallic bond is there, and crystalline structure, good conductivity is there, and they are quite ductile and chemically unstable. In ceramic matrix composite, their properties are generally predominantly crystalline or amorphous structure is there, or semi-crystalline it may also be, and poor conductivity. Ceramics are poor conductor, non-ductile, they are very hard and brittle, and chemically stable. And polymer matrix composite PMCs, they are basically predominantly homopolymer and dipolar bond, amorphous structure, poor conductivity. So they are used as insulator basically, high temperature ductile and chemically stable. Okay. And key characteristics, basically we are using alumina oxide, which is also called alumina, that as the reinforcement. So, and aluminum is the matrix material. So, what are the basic properties of aluminum and this alumina, by due to which they are widely used? So, aluminum has a basically lightweight. Its density is 1/3 of that of the steel. High resilience, corrosion resistance. As we know, aluminum oxide film is formed on the surface, which is very has a very high corrosion resistance, which prevents further oxidation. So that's why aluminum has a good corrosion resistance and good forming and fabrication characteristics, can be easily formed, and various forming operations can be done on aluminum easily. And high crashworthiness. Crashworthiness means usually they perform better in crash. If the automobile is crashed, their performance, that is damage, will be lesser. So that is basically crashworthiness. And good low temperature properties, recyclability, thermal and electrical conductivity, and reflectivity. So these are the good properties of aluminum. Because of that, aluminum is widely used in the composite material. And then aluminum oxide, which is called alumina also. So that also have very good properties like chemically thermally stable, high melting temperature about 2050 degrees centigrade, high hardness, relatively good strength, high hot hardness also, that is hardness at high temperature, then high dielectric constant, and high bulk modulus and dielectric strength. So because of this good properties, if we reinforce this alumina in the aluminum melting, we get better mechanical and various physical properties. Now the aluminum oxide nano-composites, due to their lightweight and high specific strength, particularly reinforced aluminum nano-composites are attractive structural materials for various domains such as in automobile, aerospace, defense, sports, and various other recreation and other applications. Owing to the low density, low melting point, high specific strength, and thermal conductivity of the aluminum, a wide variety of reinforcement materials such as aluminum oxide, silicon carbide, B4C, aluminum nitride, silicon nitride, titanium carbide, TiO2, TiB2, and graphite have been reinforced into it. So these are the various type of reinforcement we can use. But SiC and aluminum oxide are most commonly used because they have good properties. If compared with the pure aluminum, 2 volume% nano alumina addition improve yield strength to about 66%, hardness to about 50%, and tensile strength to about 80%. Heat treatment of the aluminum with aluminum oxide nano-composite like solutionizing and phasing are beneficial to improve the micro-hardness, UTS, yield strength. Porosity level is reduced with the increase in volume percentage of alumina. Wear rate is lower under load of 20 Newton, but increases after this value remarkably. So we will basically also, we have fabricated auto parts, various auto parts we have fabricated like gears, cam, connecting rod, crankshaft, and many more parts we have fabricated using. So particularly this presentation we will focus on the gear for automobile basically. Spur gears will be fabricating for automobile as an automobile component. So what is basically spur gear? Spur gear is the simplest type of gear manufactured and is generally used for rotary motion transmission between parallel shafts. The spur gear is the first choice for the gear except high speed and load and ratio direct toward other type of gears. Wherever speed is not very high, we prefer spur gears because they are the simplest one and easy to manufacture. Spur gear are characterized by teeth perpendicular to the face of the gear. Spur gear are by far most commonly available and are generally the least expensive. They are cheap very. Then I discuss little bit literature survey that we have done. So some of the paper I will discuss. Effect of weight percent of aluminum oxide on density and hardness of the nanocomposite. So these are the graph from various literature. So we see in the first uh, left side graph, relative density is shown with the weight percent of nano sized aluminum oxide. So we see that first density increases and then it is decreasing. Because at generally, and it is about at 3 weight percent nano alumina, we are getting the highest relative density, and after that it is decreasing. So basically, it is due to more porosity is formed when we mix more than 3 weight percent. Actually, most of the property are very good at about 2.53 or about 3.5 weight percent of alumina. And after that, most of the properties goes on decreasing. That and reason is mainly because at higher weight volume percent or weight percent, the proper mixing does not take place. And also, while if we suppose we fabricated by casting, so basically after 4 weight percent, generally the melt rejects the particles. That is, volume of particle is too high, even at 4%. So that does not mix and does either settle on the surface bottom or float on the surface. And also uh, basically segregation takes place. Because of that, properties get go on decreasing after 3 or 4 weight percent of the nanoparticles. And the other graph is showing Vickers micro hardness values. Here also we are getting at about 4.5, we are getting best highest value, and after that it is decreasing. So everywhere mostly first properties increase and then it goes on decrease, because at higher weight percent segregation takes place, particle does not mix, and bundles of particle are formed, which are the reason for the reduce of the properties. And these are the showing micrograph on mechanical properties with weight percent of aluminum oxide. So these are micrographs are showing that some dimples are there, some showing some porosity, and the right graph is showing the strength with variation of the weight percent of the nano aluminum oxide. So the below curve, bottom curve is showing the yield strength, and upper curve is showing the ultimate tensile strength. And this dark uh, triangle, this triangle are showing the proper value for the pure aluminum, aluminum pure aluminum tensile and yield strength. So this square is showing the basically about pure aluminum is having about 80 megapascal, and when we reinforce with nano aluminum oxide, the strength first goes on decreasing, and at about 4 weight percent we are having highest yield strength and also highest tensile strength at about 4 weight percent of the nano aluminum, and after that it is decreasing. And of course, tensile strength is higher than the yield strength. These are also basically these are the powder particle morphology, a micrograph of the powder while ball milling, because we can fabricate composite by ball milling also. We have although our work is concentrated on the casting method, but powder metallurgy also we can fabricate the nano composite. So we have to do ball milling first with the aluminum and alumina particles. We have to mechanical alloying basically it is. So using the ball mill. So we basically what in ball mill we balls are there. There is a cylindrical container and inside there are balls, and generally we fill up to about 10 to 15 uh, percent uh, material or powder material. So we take aluminum in powder form and alumina also in powder form and run the ball mill for maybe 10 hours or 15 or 20 hours. So in between we take the sample by at an interval of 5 hours, and the morphology of the powder particle are seen from the SEM using SEM machine, scanning electron microscope. So at interval of 5 hours the micrographs are shown, and similarly Next figure is also showing micrograph of aluminum with nano alumina particles at an interval of 5 hours or ball milling. So basically, what they are showing, figures are show the change in powder particle morphology of aluminum powder and aluminum oxide particulate at magnification of 400. So first figure is showing the irregular morphology of aluminum powder with 10 weight% of aluminum oxide particulates before mechanical alloying, when mechanical alloying is not started. Second figure is showing after 5 hours of milling, the aqueous ductile aluminum particles are flattened due to the microforging result in flat plate-like structure, while aluminum oxide particles are fragmented. And the next figure, figure C, shows the cluster type of powder particle morphology. Clusters are basically formed of the particles after 10 hours of milling. The increased surface area of aluminum particle result in cold welding of the powder component, while the aluminum oxide particulates were entrapped along the cold welded interface of the aluminum particle. So these are basically showing, I just show again. So these are the flattened aluminum part and aluminum oxide particles get mixed with these particles, and this is here we are getting just they are getting mixed again. Basically what happens, the first break, and then due to aluminum have a cold welding tendency, even at room temperature it has a tendency to weld if the force is applied between the particles. So the fracturing and cold welding phenomena takes place, and then in the final stage, in the last figure, the mechanical alloying after 15 hours, a fine homogeneous aqueous composite structure is obtained due to the fracturing of the composite lamella structure and their random welding orientation. Due to the inert gas atmosphere, the newly fractured surface was prevented from oxidation. So we have to aluminum has a high tendency of oxidation. So inert atmosphere, that is argon or nitrogen, we have to supply. The welding of the powder particles took place. So cold welding takes place. Because of that, the particles, basically aluminum and oxide, get mixed together, and we can alloy is formed basically by the mechanical means. Now this is showing variation. First graph is showing the variation of porosity with the nano size aluminum oxide content. So we see that with the volume increasing volume percent of the aluminum oxide, the porosity level is continuously increasing. At basically what happens at the particle become the point of porosity, and near the particles more porosity is assembled. Because of that, basically at higher weight percent or volume percent, porosity level is increasing. And these on the right side, the SCM micrograph are shown. Of the upper figure is showing at lower magnification, and bottom one is showing the SCM micrograph at higher magnification. So we see that the nanoparticles are quite visible in the bottom graph, and there we are showing that almost they are uniformly distributed. Uniform distribution is there. And this graph is showing the variation of ultimate tensile strength with volume percent of nano alumina. So here we see that about 1.5 volume percent, we have got the maximum ultimate tensile strength, and after which it is decreasing. And this is showing the hardness values variation with the volume percent of the nano alumina. So here also we see about 2.5 volume percent, we get best hardness, and then it is decreasing. These are the basically TEM micrographs are shown in this figure. So first on the left side we see the TEM micrograph for 5 volume percent of nano alumina with aluminum, showing agglomeration of the particle on the grain boundary. We are seeing on the grains are different grains are there on the grain boundary, particles are got agglomerated. and bottom graph also showing that similar kind of result. And on the right side, we are seeing again TM micrograph of the pure aluminum. Upper one is for the pure aluminum. This is for the pure aluminum, and the figure B next figure is for 1 volume percent of nano alumina, and the bottom figure is for the 4 volume percent of nano alumina. So we are again here also we are seeing that particles have got assembled on the grain boundaries. So these are the TM micrographs, and high magnification micrographs they are. So in TM we can get basically more magnification, and we can get a clear picture of the structure, microstructure. And these figures are showing the comparison of the ultimate tensile strength with volume percent or weight percent of the SiC particles. SiC particles are used. So first left one figure is showing the variation of the UTS with the weight percent of silicon carbide without heat treatment. So you see without heat treatment we are get quite lesser tensile strength as compared to the right one where heat treatment has been done. The right graph is showing with the heat treatment, after heat treatment basically. So this is in this right graph, we see bottom curve is showing the with ice water quench, and the upper curve is showing for with the ice quenching. So here with ice quenching rate of cooling is very high. So because of that we get more better property, higher ultimate tensile strength we have got using ice quenching, and water quenching we have got quite lesser UPS, and also it is maximum at about 6 weight percent of the SiC, and after which it is slightly decreasing. Okay. Then come to the various some other literatures. Like SS Rajvi have studied the aluminum oxide nanostructure composite powders containing 1, 3, and 7 volume percent of submicron nanometric alumina particles at reinforcement phase were produced by high energy milling. It was found that the nanometric alumina particles had a more hindering effect on the densification of the composite powder as compared to the submicron particles. The hindering effect was found to be aggravated by higher volume fraction of the reinforcing particles. And similarly, the another author, A. Shafri et al., have employed a friction stir processing (FST) friction stir processing for fabrication of the aluminum with nano alumina composite surface layer on the aluminum alloy substrate. As you must be knowing, by friction stir processing also we can make the surface composite. So aluminum work is with pre-placed nano-sized alumina particle on the surface, which was filled in a shallow groove. Some groove was formed on the surface of the aluminum alloy substrate, in which the nanoparticles have been placed, pre-placed. This groove was filled with the shallow groove was subjected to various number of, then basically rotating tool is run on the groove. So by various number of passes from 1 to 4, number of passes of the rotating tool are varied from 1 to 4. The surface nano-composite layer produced by 4 FSP passes showed superior wear resistance. This is attributed to its greater micro hardness value, because the hardness in the nanoparticle are mixed on the surface of the aluminum substrate, and because of that hardness is increasing, and because of that wear resistance also increases. So this is due to the presence of fine matrix grain and uniform dispersion of the nano-sized alumina particle. So FSP process is basically also used for fabricating. Generally surface on the top surface we can mix the nanoparticle or micron particle, but inside it remains ductile. Inside particles are not mixed. Only on the surface we get mixing of the nanoparticle by which the upper layer becomes stronger. Similarly, another author, Ali Majri and Mohsen, studied uh, different volume percent of the aluminum nanoparticle incorporated into the A356 aluminum alloy by a mechanical stir, and then a cylindrical specimen were cast at 800. So this paper is quite more related to our work. So stir casting is used. Same process we have also used in our research finding. So we have cast at about 800 and 900 degrees centigrade. And characterization of the mechanical property revealed that the presence of nanoparticles significantly increases the compressive and tensile flow stress at both casting temperature. Uh, the highest compressive flow stress was obtained by 2.5 volume percent of nano alumina particles, as I told earlier also. About 2.5 to 3 we get better properties. So then the characterization of the mechanical property revealed that the presence of nanoparticles significantly increases the compressive and tensile stress at both casting temperature. Usually effect of casting temperature are also here studied, two different casting temperature, 800 and 900. The highest compressive flow stress was obtained by 2.5 volume percent of nano alumina particles. Then again the another author, Martin Belov et al. Presented characterization of the various powder metallurgical routes, extrusion, forging, and HIP. HIP is basically hot isostatic pressing, and then sintering. Effect of the fracture of the native aluminum oxide layer present on the surface of the ultrafine atomized aluminum powders was studied. So it is shown that the different distribution, morphology, and interconnectivity of the in situ introduced aluminum oxide dispersion strongly affect the thermal stability and mechanical uh, and thermal property of the subsequent powder compacts. So here basically in situ process was used to fabricate the powder. Basically the aluminum oxide is formed inside the metal by in situ process. Similarly, Hafez Ahmad et al. Studied the high energy vat ball milling employed by to synthesize the nanocrystalline aluminum 6063 alloy powders reinforced with 1.3 volume percent of aluminum oxide, 1.3 volume percent of yttrium oxide, and 0.65 volume percent aluminum oxide, 0.65 volume percent yttrium oxide at nano size level. So two reinforcement are used here. So this we can call it hybrid nano-composite. The XRD results showed that the crystalline size of the aluminum reaches 53 to and 37 nanometer respectively after 40 hours of milling. So they have done milling up to 40 hours in case of pure aluminum 6063 and aluminum 6063 and the 0.65 volume percent aluminum, 0.65 volume percent yttrium oxide nano-composite powder with uniform particle size distribution. So this is basically powder metallurgy method. Then similarly, other author Tabander Khurshid et al. In their study, aluminum matrix composite reinforced by two sides of aluminum particles, 35 nanometer and 0.3 micrometer. Nano and micro both are compared basically, are prepared by vat attrition milling. So attrition ball mill basically, attrition milling means attrition type of ball mill was used, and hot forward extrusion process was used to manufacture. It is found that by increasing the nanoparticle content, the hardness and strength of the composite first increases and then decreases when the amount of particle exceeds 4 watt%. So as I told, at 4% up to 4% we get better property, and then after 4% the property get deteriorated. The reason is basically agglomeration of particles takes place and improper mixing, and especially particles are not mixed above 4 weight percent. Similarly, another author studied mechanical milling used successfully to disperse nanometric alumina in the aluminum matrix. So Al-2,3 aluminum nano-composite powder have been produced by various alumina size. Different sizes were used and concentration also. The 10 volume percent nano alumina powder displayed hardness values near 5 times higher than the pure unmilled aluminum. A decrease in the aluminum oxide particle size from 400 to 4 nanometer has increased the nano-composite powder hardness by 11%. So, as compared to 400 means basically 4 micron, 0.4 micron, and they have compared the micron and nano composite. So, here nano composite they get 11% higher hardness value as compared to the micron composite. Similarly, A. Mazari et al. Studied this, have worked on the development of high performance A356 nano alumina composite. It was revealed that the presence of nano alumina reinforcement lead to the significant improvement in the hardness, 0.2% yield strength, UPS and ductility. So as we see some of the literature we have studied and we got the similar kind of result in our study also. So I will skip this literature now. I come to our work. Research objective of our doing ultrasonic analysis and preparation of the automotive component, that is gear. Gear we as a for automotive application we have fabricated also using this nano composite based on the optimum composition. Then heat treatment of the nano aluminum composite automotive gear was also done, and the effect of heat treatment was also studied. And we